behind now. All right, so this is fundamentals of spectrophotometry. Really, there isn't a whole lot of differences when it comes down to language between spectrophotometry, spectrometry, whatever, okay? Basically measuring the spectra of light, right? Okay, so spectroscopy is going to be the theoretical approach of the science of studying the interaction between matter and radiated energy. I will note that the terms actually have different meanings. Each of these terms, I'll have you learn it, but you're gonna, after you get out of here, everybody will use it interchangeably and you won't know what the fuck they're actually talking about. Okay? So, spectroscopy, theoretical approach to the science of studying the interaction between matter and radiated energy. Spectrometry is the practical application of the spectroscopy. It's literally the measurement. You can remember that by metry, right? Literally metry as in measuring it with a ruler or something, right? Which it used to, by the way. You used to do gratings, and it would literally be gaps that would bend the light. We don't do that anymore, but spectrometry uses instruments. Those instruments are going to be referred to as spectrometers. Notice the similarity in the namings. Literally the thing that does this, right? Okay. Spectrophotometry. This is going to be the method used to measure how much of a chemical substance absorbs light as a beam of light passes through a sample solution. So this is an even more applied portion to this, okay? Notice this spectrometry does not have the photo in it, so you are not necessarily measuring packets of light here, okay? You could be measuring a variety of things, actually. This field has really expanded over the last 100 years. Spectrophotometers are going to be the instruments that are used in the quantitatively measure the reflection or transmission properties of a material as a function of wavelength, which would be a spectrum. By the way, this definition here is a little bit contested, okay? You can also look at degradation of, rather than just transmittance or reflectance, okay? Degradation, so you let it absorb it, and then you see how it falls down, okay? And it doesn't necessarily have the same light coming out as it puts in. So there are people that use a more broad definition for this. So this definition here for spectrophotometers can be broadened.
So you kind of go over the definition of spectroscopy.
Basically, look at it like this. Theoretical, scopy, theoretical. Meter, actually measuring it. Okay, this is the practical application. If you do it quantitatively in these methods here, then that's what they mean, okay? So the photometry is going to be looking at how much of a substance absorbs light and getting a quantitative amount, okay? And that doesn't necessarily mean you want a quantitative amount, like you're going to get that this is percent of this, but you're going to be getting a quantitative amount that's measured in units. And you may just be comparing those to figure out the identity of something, but you'll still get, you know, this has this absorbance at this position, okay? Okay. This is basically the overarching concept of this, but you can do much more than just have it absorb light. Okay? Theory, application, broadest, less broad. Okay? Yeah. Yes. Yep. So we're kind of going, here we're going the overarching concepts. Those are just two different overarching. They're not one within another. And then we're going less and less broad. Okay? And notice that basically it breaks down to the meters are just what you're using to actually measure. It's the instrument, right? And you put ist at the end, spectroscopist, if it's the person doing it. Okay. There you go. I've never actually heard anybody use spectrophotometerist or spectrophotoscopist, but I guess you technically could. Usually we just stay at this level, the overarching level, okay? This could be everything from your eyes to an NMR, by the way, at this level. Literally, you seeing would make you a spectrometer. Yeah, just be a very poor instrument. In fact, Raman's Nobel Award-winning publication that won him the Nobel Prize, Raman spectroscopy, is what he quote-unquote invented. Not really, but he was one of the guys that did work on it. Is 1 page long, and he uses his eyes as the photo detector. Well, he was in India, so. Okay. So you already know most of this, but this is kind of a review. We're going to try to go fast, okay? So we have wavelength, lambda, right? And that's your linear distance between the successive maxima or minima. It doesn't really matter, okay? In fact, one person's maxima would be another person's minima. Do you get the idea there? Basically, it's in phase, out of phase when you look at electrical, right? So it depends on what you identify as in phase or out of phase. Right? You could have it either way, it doesn't really matter. Okay? It just matters if you have two waves over each other, right? Frequency, typically denoted by a V, but it's actually the little V with the tail is the correct way. But everybody uses a V, because fucking V with the tail is impossible to put in. Is the number of oscillations of the field that occur per second. It has units of a time to the -1, typically seconds to the -1 in spectroscopy, which would be hertz, right? Notice, by the way, this is a very broad definition. This could be a hell of a lot of things. Like there's a frequency of your engine, right? There's a frequency of the ceiling vibrating, right? So this can be a very broad thing. This is actually how electric and magnetic fields work. If you're ever curious, you have one in one phase, and then you have one that's in a different plane. Okay? They're never in the same plane. And if you're ever wondering, the power from electricity does not flow through the wires. It flows through the magnetic field around the wires. Okay? So a lot of the power we're talking about here, the actual energy, is flowing in the magnetic fields around many of these things. The product of the frequency times the wavelength is going to be equal to the speed of light. And this is going to have this value right here, which is 3 times 10 to the 8th, right? Meters per second. There's the formula for it. I would never bother memorizing the stupid formula. You have meters, distance, right? Wavelength. You have seconds. Well, 1 over seconds is hertz, isn't it? You don't need anything else. Just remember the damn units, right? Okay. An interesting side note to this is that why this works like that and why this is set up like that is that unlike physical objects that have mass, stationary mass, I should say. Light does not have stationary mass. It only has a very, very, very tiny amount of mass, theoretically, when it moves. Okay? Which means that it popping in and out of reality is this wavelength. Okay? That frequency and wavelength is it's popping in and out of reality. You know, everything in the universe pops in and out of reality, right? Whether it's electrons, where we can actually see it, and we've talked about that before, right? That it pops in and out of reality. Yeah. Okay. Everything in the, let me go ahead and step back, in case anybody forgot. I guess a lot of you didn't have me for general chemistry where I would have talked more about this. I talked about it a little bit in organic, but we're rushed. So everything in the world pops in and out of reality based on what we consider reality, the universe that we consider as being it, based on its mass, okay? The higher the mass, the faster it does it, and so you cover very short distances when it does it. And so you don't see the difference, okay? So for like a proton, you can barely even detect it. It's already too much mass. It's doing it so fast in such short hops that you can't see anything, okay? You have to have incredibly, really intricately designed experiments to do anything to detect it, all right? But you can. And there's a lot of explanations on why this happens. I'm not going to get into that. It's theoretical, and it gets a little bit complex, okay? And we can talk about it sometime if you like. But that's how the universe actually works. It's kind of like a film, right? You get frames flashing really fast, and it looks like it's a constant image. Okay, so when you get less mass, like an electron, you actually see that. And it will literally pop such large distances that you can actually pop all the way from like one side of an atom to another, okay? Or from one circuit to another if you get into the picometer circuits, okay? Is that making sense?
Yeah.
And that's what's called quantum tunneling normally. That's all that is. It's just electrons are so light they can pop from one place to another. It's enough distance to actually do stuff, okay? When you get to light, it has no resting mass. It's considered to have mass when it's moving. Not that we've ever had frozen light, so God knows.
The mass of light is pretty much
No, it's way lower. It's because it's a packet of energy. We consider it energy because it essentially has no mass, or such small amount of mass that we normally would never detect it. Okay, but it does have mass. It gets pulled by gravity fields, like light bends around black holes and stars. But it's so low mass that even a star can barely bend it. Like a thing that an electron would get pulled into the star, the light would only get pulled maybe 1 degree off course. So the electron would go 90 degrees off course, light would go like 1 degree. It has such low mass, even when it's moving. Yeah, there is. Yeah, there's ways of measuring it. I just don't want to go so far off on that topic, okay? It's so far beyond an undergraduate degree that, like, we're talking PhD level shit, okay? This is not something you would normally get in an undergraduate degree. We'd have to have a whole course on just getting you ready for it, okay? This is just, like, this is beyond quantum, what a normal undergraduate quantum level would be. This would be like 2 steps past that, okay? Okay. But yeah, I mean, it has mass. Like, you may have heard of like a solar sail. Yeah. And those are literally pushed by that energy and mass. But the reason we consider those packets of energy is because we're looking at a sliding scale. It's not actually a sliding scale, it's a step scale. It has very small steps. That's why quantum. That ranges from almost all energy, pretty much no mass. We can't even measure the mass if it was sitting still. In fact, it probably just ceases to exist. I have no idea what the hell light sitting still would be. Hasn't been done yet. I've never seen it. And then we have something that's almost all mass right now. It's expressing almost none of it as energy. Okay? And that would be like a large mass of something at 0 Kelvin. Okay? Like Bose-Einstein condensates, that sort of stuff. No. No, it'd just be a very, very low energy crystal, essentially.
Oh,
Yeah, where you've like frozen everything in place. Okay, and even then, we haven't ever gotten to zero energy. Not even close. So even at 0 Kelvin, sucking out all the energy we can, there's still things like small amount of vibrating would be. Once we get to 0 Kelvin, we'd have no vibrations theoretically, but we still have like the microwave spinning and stuff. Yeah. So rotational energy and yeah. Anyways, we probably can't get to zero energy or zero mass. That probably isn't a thing. That probably is what makes something exist in this universe. And there's some really advanced work that's been done, but we're talking bleeding edge of science right now. Nobody has any fucking clue what's going on yet. Okay. Once we crack that, it'll be a big deal. Okay, so again, photons are going to be particles of light with energy. They're the most pure expression of energy in this universe right now. Okay?
So, all right. Mm-hmm. So what you're saying is this.
I know it's fascinating, right?
The most fascinating scientific discovery is finding absolutely nothing.
Mm-hmm. No, I mean, that's actually kind of how science works, right? Yeah. And you know, the biggest scientific discovery that won the Nobel Prize this year in physics was that things don't exist. Know that? Yeah. There's no local representation of something until it's interacted with. So like when you have several energy states it could be in, it doesn't collapse down into those energy states, which is what we normally consider existing, until it's interacted with. Typically, they call that observed. That's a language that comes from like Einstein back in the day, because you know the observer was doing it, but it doesn't actually need a person there. Like if a particle hits something, it's going to collapse down into a state. Okay, and that particle could be from the sun or it could be from you. Right? Whatever. Hey, Emma. There we go. We had a hell of a discussion. You're going to have to listen to that one. Like, oh, and by the way, did you guys know imaginary numbers are real? You know the square root -1? Those represent actual states of the universe. There are actual states of the universe that exist that are described by imaginary numbers. So imaginary numbers, not so imaginary. I know, right? Okay, so E equals Planck's constant times the frequency. This actually is telling you that this Planck's constant, that's actually the representation of that popping in and out of existence, if you're curious. Okay? But nobody understands exactly how that is yet. But it's on all of these equations that represent that. Okay? So, yeah. We're just going to move on and act like we know what's going on. Okay, cool. Basically, spectroscopy is where we use the thin layer of our human understanding to explore everything else. And we get to see the hints of what the fuck is happening. That's the beautiful thing about spectroscopy. It's also where you get to use your imagination. Like, spectroscopy is the field that takes the most imagination and creativity, where you get to just come up with things on your own. Like, I think this might be, and then you test it, and oh, I was wrong. I think I might know better than everybody else in the universe. Nope, I was wrong. Or, oh, didn't find out I was wrong yet. Maybe I was right. Okay, so if we combine these two equations, we actually get the energy of photons. Okay? And that's this. Planck's constant, speed of light. Then you can divide it by lambda, or you can reciprocal. Okay? You can solve this. So by how many kilojoules per mole is the energy of O2 increased when it absorbs ultraviolet radiation with a wavelength of 147 nanometers? This would be a pretty common question that you might get. And what you would do here is, well, you want energy, right? And so you take this nanometers, you get into meters, right? That would be your wavelength. Speed of light's a constant, h is a constant. That's all. Do you need this formula? Hell no. Joules, that's energy, isn't it? Per second, well, we can get that from the speed of light, don't we? That cancels out seconds. Meters will cancel out the meters and speed of light, and we'll be left with joules, won't we? There you go. Okay, these are the properties of light. You guys didn't have me, you did, Emma did, which you may not remember. I do this in general chemistry as well, okay? And this is actually something that most people don't really understand very well, but whatever, we'll go with it. Okay, so these are the different types of frequencies of light, their wavelengths. These are somewhat artificial separations between these boundaries that have just been created so people have nice pockets to put stuff in, okay? But the overall gist of this is microwave and radio are pretty much the same thing, okay? There's not really a lot of difference. Microwave and radio have such low energy that basically what you get out of this is rotation. So if you were to hit a molecule with microwave radiation, you get rotation. Now, certain materials, if you hit it with microwave radiation, this can also transfer to vibrations, okay? Which is like radio. That's how old radios worked with the crystals. They literally would vibrate that, okay? And that's also how a microwave at your house works. You hit it with the specific radiation that triggers water to rotate. If you do that enough, the water molecules hit each other and start bouncing all over the place, which is heat, right? Which is why if you ever get something very fatty, it won't heat where the fat is. It only does it where the water is. Also, like metals, if you do this with metals, you'll cause electrons to be ejected. You'll cause ionization with microwave radiation, which is why you can't put metal in microwave. Okay? Infrared, this region typically causes vibrations. Again, remember typically, we're talking mostly organic molecules with this sort of stuff. Non-metals typically. The infrared is going to cause a vibration of a molecule, and this can be many things. This could be like stretches. So say you have two atoms, they'll stretch back and forth, come in and out from each other, and change that bond length. Okay, that'd be a stretch. You can also get things like bond angles changing. Okay, and that'd be deformation is what that's called. Anyways, these are both regions that I am an expert in. Okay, a very high functioning expert in. This right here is visible. Visible is just called visible because the majority of humans can see those. Okay? That's it. It doesn't have anything special about it. It would really be divided between the infrared. By the way, infra meaning lower, red, below red. That's lowest energy visible. And ultraviolet, ultra meaning above, violet, just the highest energy visible light. Some people can see in the ultraviolet and near infrared, by the way. Some women. Men don't. I know. Sucks, right? Okay. But anyways, and for example, there are shrimp that can see down into the microwave all the way up into the high levels of ultraviolet. Okay? So this region down here is typically the vibration region. This region up here would be up here with the ultraviolet, okay? In terms of what it does to molecules. So what does ultraviolet and the higher level energies on the visible do? Well, they're going to excite electrons. And this is actually how color absorption typically works, okay? So what it does is when the photon comes in, it gets absorbed, it boosts an electron into a higher level orbital. Remember the orbital diagrams we did for molecules? Molecular orbitals? Yeah, it's that. So it would boost an electron up into one of those other orbitals, and it would leave the orbital with one electron short. And then it'll fall back down. When it falls back down, it releases a photon. Okay? And you seeing that released photon is colored. Like my shirt is blue. That's because it's releasing blue photons. Because there's an orbital that matches that. Okay? Okay. All right, so please note that you don't have to absorb and release the same energies for photons. In fact, that's how Raman works, and that's why the sky's blue. Okay? You can actually release photons that are slightly different energy. All right. So this right here is X-rays. So again, remember that when I said this is somewhat artificial limits. There are things that are going to do this up in the upper ultraviolet region. Okay. So X-rays will actually cause bond breaking and ionization. So instead of exciting an electron into a higher energy orbital, it will eject the electron. Okay? And that will cause ionization. And typically it also causes bond breaking because remember, a lot of these molecules, your higher energy bonds that ejects, are going to be ones that are involved in the bonding, right? So they would have been electrons in the bond, and that would decrease the bond order and cause the bond to dissolve, right? Separate, because there's nothing holding it together then. Okay? Okay. Keep in mind, though, this is that bond ionization energy. Remember that from Gen Chem? Where we had like a little periodic table, and it gave us energies for ejecting things from the atoms. That's actually the same stuff there. Okay? One of the things people get confused on is like these would be the energies that would do it for pretty much everything, most things you'd encounter. But like metals will actually eject electrons and ionize using microwave radiation because they have such low bond ionization energies. So this is just like a scale to help you out, okay? Gamma rays, everybody knows gamma rays, right? Okay. This will just do the same stuff as X-rays, but much, much better. Okay? Think of it a bit like you're jumping up stairs. Okay? So if you have a short jump, you can only jump up very small stairs, right? And that would be these. If you have a much higher jump, then you could jump up whole floors, right? Kind of like Superman. And if you have a high enough jump, then you're going to jump over everything, right? So you'll just pretty much detonate the molecule when you hit it. Because you'll break a bunch of bonds and eject electrons everywhere, and those damn things will do whatever. Okay? Does that make sense? Gamma rays is actually where this stops. Theoretically, if we found high enough energy, we would still be in gamma rays. But this does kind of have a limit that we haven't found stuff above, okay? But it does have things like cosmic rays, gamma bursts that come from stars. This is very high energy. We haven't yet detected stuff that's beyond that, and that actually might be a thing. So this would be interesting. Anyways. All right, so this is the absorption of light. When you absorb light, you're boosted up into a higher energy level. This is called an excited state. Clearly, it's excited, right? When you drop down from a higher energy level to a lower energy level, that would be an emission. You emit a light then. The direction you absorb and emit have nothing to do with each other, and you don't necessarily have to emit the same radiation as you absorb. Okay? Notice these here. None of them are the same, are they? See that? There's a bunch of them that are different. Huh? Okay. So the energy of a molecule increases when it absorbs a photon. When light is absorbed by the analyte, the irradiance, which is the energy per second per unit of area of the light beam, which is denoted by a P, by the way. You can think of that as power. okay, decreases. When monochromic light monochromic meaning one color, so that's light that consists of one wavelength. You never actually get one wavelength, you get a small spread of wavelengths, but essentially we're trying to get one wavelength, right? So when the monochromic light with an irradiance of P0, so the starting irradiance, strikes the sample, the irradiance of the beam that's emerging is going to be P. So P is always equal to or less than P0. It would be very unusual actually for it to ever be equal, by the way. Typically most things would absorb some energy, but it does happen where you don't absorb any energy. That is possible, okay? Unlike most things in the world, you can actually get equal, right? Which means that it doesn't interact essentially. Okay, so this is the basic setup of all spectrometers, okay? You have a light source, a source of your irradiance. You have some sort of wavelength selector. This can be referred to as a monochromator, okay? Or a monochromator. This is where you would measure P0 after the wavelength selector, okay? This entire purpose here is to select for a very narrow range of wavelengths so you can control that wavelength. By the way, the spectrometer, the infrared spectrometer you guys have used, has a variable wavelength selector. What does that mean? You select a wavelength, measure, select a new wavelength, measure, select a new wavelength, measure, okay? You do that over and over and over and you make a line. And that's what that, peaks and valleys and baseline and all that is, okay? Okay, so P0, this is going to be the irradiance. Essentially, it's the amount of energy per that area that strikes your sample. You will then have a sample, it will have a path length, and that will reduce P0 by some amount, by absorbing it, right? If your light wavelength does not interact with your sample, you'll get P0 again, right? You can never actually get higher than that, okay? If you get higher than that, then you've mismeasured P0. There's something wrong, okay? It happens, by the way. Sometimes you do these measurements. You'll have a P0 that you think is right. You'll measure the P output, irradiance output, P, and you will get a number that's higher. Do you know what that means? You can actually use it for things. Like, there's a technique for ramen that you actually do that. And then you take that difference, and that gives you a spectrum. Okay? So it's not necessarily a bad thing if you know what you're doing. But you gotta know what you're doing, right? Yeah. It's not uncommon for people to have energy that they don't take into account going into a system. Okay?
What is the B for the sample?
Oh, B is path length. Yeah, remember Beer's law? That's the path length in Beer's law. So what determines how much P goes down is going to be Beer's law. Okay? Essentially, for most applications. I'm not going to go into a whole lot of other stuff because I could teach a whole degree on that. But yeah, remember then that's path length, concentration, times the extinction coefficient, which is how well it absorbs that light. Okay? By the way, the extinction coefficient would have to do with these energy levels. That's a sort of sum term that says this matches those energy levels really well. Okay? And so it absorbs really easy, and it goes up into an energy state that can very easily happen. All right, so you notice that we haven't been talking about absorbance and transmittance yet. These are derived terms. Okay, so transmittance is going to be the fraction of the original light that passes through the sample. So 100% transmittance would be getting P0 back out, right? Notice that in your spectra that you've been taking in lab, if you go back through them, you'll actually see places you have higher than 100% transmittance. What did that mean? He got more than P0 back out, didn't you? Yeah. And that's because the P0 is set by the background. And so your background's in error, or you have a different condition. Okay? Which happens because, like, you know, it warms or cools and your crystal absorbs light differently, right? So you get all sorts of things that can affect this. But if you understand what's happening, you can know, you know, oh, it's a 0.01%, who cares, right? Or you can know what is causing it. And that's what we're trying to build up here. So you know when it goes wrong and why. Okay, so transmittance is going to be P over P0. It's literally the percent. Percent transmittance is just making that into percentage, right? Okay, now you may have noticed that Beer's law and everything are typically done in absorbance. Absorbance is going to be a logarithmic scale of transmittance. It is a P transmittance. Remember pH, PE, how we did all those? Negative log of. That's what absorbance was all this time. So absorbance, A, of the solution contained in a transparent cell having a path length of B would be Beer's law. Okay? Notice that the absorbance of the cell is actually factored into this P0 by our backgrounds. Okay? So nothing ever absorbs is transparent completely. Typically you have some absorbance, but we're getting rid of that because we're factoring that into P0 by taking a background. Okay? By the way, your book does not mention that. That's why you guys pay me the big bucks, right? Whole $100. All right. So absorbance equals extinction coefficient. That's the B, path length, was mentioned here. And then C is a concentration. Okay? Fantastic. By the way, the extinction coefficient units has to match your concentration. Be careful, because I have seen non-molarity extinction units. Okay? They do exist. All right, so relating transmittance to absorbance. Well, this is the relationship right here. Absorbance is just the negative log of the transmittance. And so it would be also the log of P0 over P. You guys got how we got P0 on the top here? Negative. A negative before a log would flip the stuff inside. Okay. Okay. So literally it's a PT, isn't it? Lowercase pt. Yeah. Just like a pH would be. It's a logarithmic scale of that. And that's because transmittances are logarithmic scales, right? If you take a log of it, you'll get a more linear relationship, which you need for Beer's law, right? Because you plot that as a linear relationship and get a slope, right? So absorbance is proportional to the concentration of the light-absorbing molecules in the sample. And again, that's because that's that logarithmic relationship. Remember that, okay? The part of the molecule responsible for light absorption is actually called a chromophore. Literally something absorbing light. Chroma, light, right? The different colors of light. For, something doing it. So, chromophore, it's the colorful stuff. Colorful because it absorbs light, right? Okay. The example here would be finding the absorbance and transmittance of a 0.00240 molarity solution of a substance with a molar absorptivity of this right here in a cell with 2 centimeter path length. So what would you do? You take this, multiply it by absorptivity, Molar absorptivity being the same thing as extinction coefficient. It's the E, that little E thing. Okay. And this path length is 2 centimeters, which by the way is very unusual. Most path lengths are 1 centimeter. So the equation's easier, right? Notice the centimeters canceled, the molarity is canceled. You're left here with your absorbance. Okay? Absorbance is always a unitless number, isn't it? It has to be. You're taking a log of it, right? And transmittance is also always a unitless number because P over P, right? It cancels its units. You're just a percent transmittance, no units. Okay? One of the interesting things about transmittances and absorbances, unless you have something to measure against internally within your sample, you cannot compare transmittance and absorbances to each other. Okay? You need something internally setting that standard. If you take the spectra very quickly, one after another, you'll be able to compare them. But if you took them on 2 different instruments, or at 2 different times, or you had a variation in your electricity going into there, which happens all the time on a grid, right? They would have different absorbances, okay? Because again, they're unitless numbers that are relative absorbance from that power, right? So anything that changes P0 is going to give you a different unit. Okay? It'll give you different absorbances, different transmittances. Beer's law is a limiting law. So it's going to apply to a monochromatic light. It applies to dilute solutions, which would be under or equal to 0.01 molarity. Notice that is very dilute, right? Did you guys remember our spectroscopic analysis that we're doing? Where we had you dilute it to a very dilute solution, didn't we? Why is that? Because Beer's law will apply, right? Why is this? Remember when we looked at the limit of detection graph? That dynamic region, limit of detection, linear region? Okay. The linear region only exists for dilute solutions, right? Once you get higher concentrations, you're in dynamic region, but it's no longer linear, is it? And so you can't use Beer's law, okay? It fails if the analyte undergoes a chemical change, and the product of this change has a different spectrum than the original analyte. You could actually make a Beer's law for the product. But yeah, if you have a different species, you're going to have a different Beer's law, right? Okay. Beer's law will fail when deviations from the proportionality between measured absorbance and concentration occur. I've given you a few different reasons why that might occur, right? Can you make a Beer's law and expect a year later for that instrument to have the same Beer's law with that substance? No, definitely not, right? Because your conditions in your lab will change, won't they? And remember, Beer's law depends on P0 staying the same throughout all these measurements. If P0 changes, all of your absorbance changes, right? Okay. And P0 changes with things like temperature. It changes with things like moisture level for many spectroscopy techniques. It changes with CO2 concentration. So guess what happens when you're sitting there for 3 hours measuring things? Your background changes, doesn't it? Meaning your P0 changes. Okay. By the way, this is the most common mistake done in industry, if you're curious. The most common way to screw up an industry is that they will take a Beer's law, they'll do all that work, backgrounds, Beer's law, everything, and they'll do it like a week, once a week or once a month, and it's not, it's too long of a duration. You can't use it for that long. And so they'll get incredibly inaccurate measurements later on. Or, one day the moisture levels will change, or the temperature in the lab changes, or whatever, and they'll get crap measurements, okay? Or even they'll take it in the mornings, and they have an instrument that's responsive to CO2, and so people will work, they don't have good enough ventilation, and those CO2 levels will rise because people are working, breathing, right? So you have to keep things in mind. You can tell that. Remember, we gave you a bunch of tests at the beginning of ways to tell that. You would just take a known standard and work it at different times of the day, right? Which is why a good corporation will have a standard that they would scan when they do all their other results. Remember how we talked about that? You can set up do 4, and then one's a secret internal standard that you don't tell the people. If they screw it up, then you know all your other results are wrong. This will help with that, okay? These are all systematic errors. So anyways, figure 18.5 shows the minimum requirements for a spectrophotometer, excuse me. The light from the continuous source passes through a monochromator, which will select a narrow band of wavelengths from the incident beam, the incident beam being the one that goes into the wavelength selector. Okay, are you guys okay with me going back and forth on that term? Okay. So incident being before you do something to it, and you're going to select a narrow range of wavelengths. You never actually get a single wavelength, okay? It's just not possible. Nothing ever works that nice, right? It actually is theoretically possible, I guess, but due to the uncertainty principles, I doubt you could ever actually do it in this universe. Okay? Anyways, you get a very, very, very thin slice of wavelengths. This light coming out of the wavelength selector will then pass through the sample path length, and the irradiance of the emerging light will then be measured, and that's your detector that does that. For visible and ultraviolet, a liquid sample is usually contained in a cell called a cuvette, and that's that 1 wavelength, 1 centimeter cuvettes that you guys are using. Typically made out of quartz or glass. Quartz is better, or plastic. Again, quartz is better. Which I think we actually have quartz ones now, which are quite nice. Cuvettes are typically made out of things like fused silica, SiO2. Glass is okay for visible. So glass will work for visible light. And those may be glass. I'd have to look in the spectrometer. If they are, they're very high quality glass. Because they're actually pretty nice ones. However, can you get a suntan sitting in front of the window?
This window or
Any window. No. Glass absorbs UV radiation, right? So any window with double pane window will absorb 90-something% of the UV radiation. Okay? And so no, you can't get a suntan or sunburn sitting in front of a window. You also can't take UV spectra with a glass cuvette because you'll lose almost all your UV radiation, right? It also causes it to heat up and re-radiate, by the way, which is a whole nother series of problems. So the most common path length, again, is 1 centimeter. These will typically be sold in matched sets for a sample reference. By the way, those are what those 4 cuvettes in a box are. They're matched sets. At least they should be. I haven't tested them, and I'm always I hate using things and not testing them. Okay, these are some different types of cuvettes and cylinders. This is a gas cylinder, by the way. This is flow cylinder. You'd flow your sample through. This is stuff that breaks down over time. Okay. Thermal cylinder. That's where you freeze it or you change the temperature of it. And that would have a thermometer, and it would also have like liquid nitrogen coming in. Okay. And these are the cells you've seen before, the microcells. Okay. Let's go ahead and stop on this next one. and we'll pick up from there next time. Wow, I'm going very slowly through this.